neurons communicate, and that is chemical communication. Understand the process of exocytosis. Know it in detail. All right? I want you guys to understand that an action potential causes voltage-gated calcium channels to do what? What happens when an action potential goes down the length of the axon? What happens to voltage-gated calcium channels? What do they do? They open, and then what happens? Calcium goes in. Why? Because it wants to reach its equilibrium potential. Always the answer, right? So, know the answer to that, and then what happens after calcium enters? This is review. Your exam is on Thursday. If you don't know the answers, you need to study like hell. So what happens when calcium goes in? Shit! What happens when calcium goes in? Are y'all panicked now? Yeah. All right, good. Be panicked. Study hard. What happens when calcium goes in is that the synaptic vesicles will go to the active zone, fuse with the active zone, release neurotransmitters, right? But the impetus for neurotransmitter release is what? I said this 5 times last lecture, or the lecture before that. What is the impetus for neurotransmitter release? What causes neurotransmitter release? Look back at your notes. Oh my God, do I need a beer? I need a beer. Does anyone have beer on their persons? Because I need an anxiolytic. You guys are making me, I'm sweating. Why are you making me sweat?
Calcium.
Calcium, thank the Lord. Who the hell said that? God bless you, thank you. Calcium, you should write this down. If it's not written down and you don't know the answer, that's an easy one. Calcium is the impetus for neurotransmitter release. And yes, I know that I have the hardest class in the psych department. Students tell me this all the time. Graduate students anyway. Calcium is the impetus for neurotransmitter release, and yes, you do need to know that. So, communication within the neuron is the action potential. Communication between neurons is neurotransmitter release. You need to know what neurotransmitters are. They're a chemical signaling molecule that is released from a neuron that then binds to what? What do neurotransmitters bind to? I heard someone quietly say receptors. Yes, that's correct. Receptors. And if you didn't know that, you need to know that. Oh, does this work? No. Can you guys see this? Yes. Yeah, here's the pointer. Okay, so the neurotransmitter binds to the receptor, and that is really what initiates what's known as post-synaptic effects. So this post-synaptic neuron, where this neurotransmitter binds to, is going to have some type of biological effect as a function of that neurotransmitter binding to the receptor. Does this make sense? All right, good. Does it feel like a Monday? Is that the thing? Does it feel like a Monday? All right. Know this. Know that the action potential is an electrical event. Which part of the neuron is the only part that can conduct an action potential? The axon, and I do believe that that is a test question for some of you. So the axon is the only part of the neuron that can conduct an action potential and is a defining feature of a neuron. Know these principles. Electrical current. That's a movement of electrical charge. What is that really referring to? The movement of electrical charge? No. It's measured in amps. What is electrical current referring to? What's moving? Ions. Yes, exactly. Very good. The electrical current, this is referring to the movement of ions, and this is measured in amps. So when we see movement of electrical charge, this is really referring to the movement of ions. What are we talking about when we talk about electrical conductance? What is that referring to? Yes, the number of ion channels that are open. Exactly. So if you have a high level of conductance, what does that mean? Lots of channels are open. Very good. Electrical potential. What is this referring to? We talked a lot about this. We spent a lot of time on this. This is measured in volts. Conductance is measured in Siemens. What is electrical potential referring to?
The difference in charge between inside and outside.
Yes, between the inside and the outside, which I purposefully did not put on that slide. So this electrical potential difference is really referring to the difference between inside versus the outside, okay? You will need to know this. And we talked about that water hose analogy. We talked about it many times, right? We talked about water flow. So this is the curve of the flow of ions. The diameter of hose really refers to it could refer to either the ease of ion flow, or it can actually refer to resistance, right? So if we have a very small diameter for our axon, that's really what that's referring to. If we have a small axonal diameter, how does this affect the flow, the ion flow? Is it going to be big or is it going to be little? Little. If you have a super tiny hose, then your ion flow is going to be little. Does that make sense? So if I had a huge hose, like a fire hose, what would that indicate? I'm going to have a much greater ion flow. Does that make sense? Okay, good. All right, so I think that's good. What does the myelin sheath do? Do you guys know? Insulates the axon, and then ultimately what does it do? It speeds up action of potential velocity. Very good. You should know that as well. Know what depolarization is. I'm going to ask you, is this a depolarizing stimulus? Is this a hyperpolarizing stimulus? So what is a depolarizing stimulus? What is that? What's a depolarizing stimulus? Yes. The membrane, the V sub M goes up. So if the V sub M goes up, that's a depolarizing stimulus. So if I tell you the membrane potential of a neuron is at negative 40 millivolts, and then a stimulus comes through and changes the membrane potential. So if I say the V sub M is equal to negative 40 millivolts, and this changes the membrane potential to negative 30 millivolts, is this a depolarizing or a hyperpolarizing stimulus?
Depolarizing.
Depolarizing, very good. So here is a depolarizing stimulus. So then what is this also called besides a depolarizing stimulus? Yeah. Excitatory postsynaptic potential. EPSP, right? Know this. All right, because I may also refer to this as an excitatory postsynaptic potential, not just depolarizing. These are interchangeable, and you should know this. So an EPSP is going to get you closer to an action potential threshold, right? Presumably, if you have a big enough EPSP. Okay? Okay, so if, for example, I have the V sub M of negative 40, right? And I change that negative 40 millivolts to like negative 80 millivolts, what type of stimulus is this? Hyperpolarizing. Why? Yes, it is decreasing membrane potential. Good. Very good. So you are decreasing membrane potential, right? So this is hyperpolarizing. What is this also known as? Inhibitory postsynaptic potential. Which of these neurotransmitters is going to cause an EPSP? Which neurotransmitter is going to do it? Which neurotransmitter? Yes. Glutamate is going to cause an EPSP. Why? Oh, look, everyone's seriously writing shit down. I love it. This is bad. We should have written this stuff down before. Do I sound like a mother? I should. I feel like a mom. All right, so glutamate. Why does this cause an EPSP? Yeah, but why? What's the mechanism? What is the mechanism? Why is glutamate excitatory? I'm asking you guys to think.
Is it because it's a positive molecule?
Not quite, yeah.
Is it the sodium enters with
Yeah. It's because glutamate opens up voltage-gated sodium channels. And then sodium goes in. Why does sodium go in?
Because it wants to reach
It wants to reach its equilibrium potential, always the answer, right? So glutamate opens up voltage-gated sodium channels. I think it also opens up calcium channels as well, okay? But this, in essence, is what causes glutamate to be an excitatory neurotransmitter. What is an example of an inhibitory neurotransmitter? GABA. Very good. Why is GABA inhibitory? Chloride goes in. Chloride, which has a negative charge on it. This negative charge in and of itself will decrease membrane potential. Does that make sense? So these are the types of things I want you to think about as you guys are preparing for your exam. The difference between inhibitory and excitatory neurotransmitters, the difference between depolarization versus hyperpolarization. We are going to talk about this again when we talk about learning and memory. This is going to be, and we're not even just learning and memory, we're going to talk about it when we talk about vision, when we talk about the auditory system. This is going to be a general principle that we will take with us throughout the rest of this course, which is why it is absolutely imperative that you know the difference. Does this make sense? Please know the difference. If you don't know the difference for the exam, then you're going to have a harder time in this class than the rest of this semester. Okay. So, understand the kinetics of the action potential. Understand the difference between absolute refractory period and relative refractory period. What is the difference between absolute versus relative?
In relative, you can fire action potential, but in absolute you can't.
Right, absolutely correct. During the absolute refractory period, you cannot fire another action potential. All right? And it's because the voltage-gated sodium channels are closed. They are not open for business during this part of the action potential. So you can only trigger the one. However, during the relative refractory period, you can trigger multiple action potentials, but it requires a greater stimulus to do so. Okay? So, what is responsible for the rising phase of the action potential? What causes the depolarization of the membrane potential?
Sodium.
Sodium. What is sodium doing? It's going in, and that is a test answer. Sodium is going in during the rising phase of the action potential. So what's happening during the falling phase?
Potassium.
Potassium is leaving, and that is what's contributing to the falling phase of the action potential. And so what then is contributing to this resting membrane potential? How is that working? The sodium potassium ATPase pump. We talked about it, guys. It's the Nick Cannon of your brains. Right? It works harder. It might work harder than Nick Cannon, right? It's a sodium potassium ATPase pump which establishes resting membrane potential. And yes, that is another test question. The sodium potassium ATPase pump is the pump that is constantly trying to establish resting membrane potential. Even through the course of the action potential, that sodium potassium ATPase pump is constantly working, shooting out 3 sodium, bringing in 2 potassium to try and reestablish resting membrane potential. Okay? And that is a test question and answer. So you do need to know this. That is a thing that is reestablishing the resting membrane potential all through the course of the action potential. Okay. You guys are doing pretty good. Know this. Know why this is important. The increase in calcium is what's causing neurotransmitter release. I'm not going to lie to you. I love this slide. I love it. I think it's fun. I like knowing this whole process. The reason why these voltage-gated calcium channels open is because they depend on what to open? I'm sorry, what? No. Voltage-gated calcium channels depend on what to open? Or just a change in voltage. A change in voltage is going to cause a voltage-gated calcium channel to open. That is why they are called that. Anything that's called voltage-gated anything, voltage-gated sodium channel, voltage-gated calcium channel, voltage-gated potassium channel, all that they require is a change in voltage. And so this voltage-gated calcium channel is going to open up because you've essentially depolarized this neuron so that this channel opens up and allows for what to happen? What happens when a voltage-gated calcium channel opens up? Calcium goes in. And this calcium, the increase in calcium concentration is what leads to this process of exocytosis. What is the definition of exocytosis? What is the definition of exocytosis? I will never have another exam review. This is the only exam review you get all semester. And the reason why is just we don't have enough time. We have to cover so much shit, we just don't have time for the exam reviews. So what is the process, what is the definition of exocytosis? Yeah, like that would be the technical definition. But what is it really? Yeah, the release of neurotransmitter. Exocytosis is the release of neurotransmitter. Okay? So, release of neurotransmitter into the cleft. This is all happening at the active zone. Okay? And you will need to know this in great detail. This whole process of synaptic vesicle fusion, whereby the synaptic vesicle, what is inside the synaptic vesicles?
Ions?
No. What's inside a synaptic vesicle? Neurotransmitter. Yeah. So once again, I'm preparing you for this exam because this is the language we are going to use for the rest of the semester. So if you didn't know that the synaptic vesicle contains neurotransmitters, please know and remember that for the rest of this class. Right. So the synaptic vesicle contains neurotransmitters, right? And so the synaptic vesicle will fuse with the active zone to release neurotransmitters. And they do so through these proteins called V-snare, which is located on the synaptic vesicle, and T-snares, which are located on the active zone of the presynaptic neuron. Right? So the synaptic vesicle will tether itself using these different proteins. Why does the synaptic vesicle have to tether itself? Why is this important?
It'll float away.
Yeah, it'll float away. Because this whole thing is filled with fluid, so it'll just float away unless there's a place for it to dock. And that is actually the technical term for it. It's called docking. The synaptic vesicle has to dock, right? People have spent, I actually know a guy who studied this his entire 40-year career. This principle of synaptic vesicle fusion, the docking of these synaptic vesicles, right? So once it fuses with this presynaptic membrane, it will then release neurotransmitters. Now, what is the process of endocytosis? Yeah, recycling. We need to recycle neurotransmitters, so make sure you know that. The other fate for neurotransmitters is that they can be broken down by an enzyme. Know this. Know that we have a readily releasable pool of neurotransmitters versus a reserve pool. Can someone tell me the difference in terms of this readily releasable pool versus this reserve pool? What is the difference between the two pools? Anyone else think of an apple? What's the difference between a readily releasable pool versus the reserve pool? Yes, one is close to it, and then
The other side of
yeah, the one is located much further away. Very good. This tells you a lot in terms of about the kinetics of their release. So the one that's the closest to the presynaptic membrane, what does that mean? Is it going to take longer to release or a shorter amount of time to release? Shorter, because they are closer to the active zone. Reserve pool takes a way more action potentials in order to activate that reserve pool. Plus, you need a lot more calcium as well to activate the reserve pool. Okay? All right. You need a lot more calcium, and you need a lot more action potential to activate that reserve pool. Right? Okay. You don't need to know this. I won't ask you any questions about this. You can. Know the difference between an agonist versus an antagonist. What is an agonist? What's an agonist? We're going to be talking a lot about agonists and antagonists. What's an agonist?
Mimics the action of the neurotransmitter.
It mimics the action of a neurotransmitter. If you didn't know that, you need to write that down. An agonist will mimic the actions of a neurotransmitter. Good example of an agonist would be fentanyl, which is a terrifying one when you think about it, right? It's horrible. Morphine is also an agonist, meaning it acts like opioids, right? So morphine will bind to receptors and have very similar biological effects to that of opioids, which we produce naturally. What is an antagonist? Yes, it blocks a neurotransmitter from binding to its receptor. So naltrexone would be a very effective treatment for someone who is undergoing a fentanyl overdose. Okay? Know this, the neurotransmitter, only one receptor, a receptor will only accept one neurotransmitter. So an acetylcholine receptor will not take dopamine. Does that make sense? No, you need to know that. So a glutamate receptor will not take GABA. It will only take what? A glutamate receptor will not take GABA. It will only take what? Glutamate. Very good. All right. I think I have a question about this one, so I'll skip it. But I do want you to know that the two fastest acting neurotransmitters are glutamate and GABA. And it is because they operate through ligand-gated ion channels. What is a ligand-gated ion channel? How do they work? You can't start talking and then cover up your mouth. I saw you, girl. Okay, go ahead, you do it. You have the right answer. What's a ligand-gated ion channel? Yes, see, that's a beautiful answer. You didn't need to be afraid. That was very good. So a ligand-gated ion channel will respond and open when a neurotransmitter binds to a receptor located on it. And then what happens is that it opens up an ion channel. So glutamate-gated ion channels, so if it binds to an AMPA receptor, which is in fact a glutamate receptor, it will open up to potassium and sodium. NMDA glutamate receptor will open up to sodium and calcium. And this is what makes them ligand-gated ion channels. GABA is another example of a ligand-gated ion channel. So GABA will bind to a receptor on this channel and then open up chloride ion channels to allow chloride to go in. Okay? All right. I want you to understand the sort of general principle of G protein coupled receptors. I'm not going to ask you any sort of specifics about the process. But what I do want you guys to know is that G protein coupled receptors take much, much longer to take effect. But their effects are more widespread. Does that make sense? So I do want you to know that. Okay. That was a really quick review. Do we have any questions? Oh, other things I want you to know for the exam. There are, like I said, there are images on the exam, and if they work, these are the images you should see on the exam. One will be the lobes. You'll need to identify the lobes. Then there's another one that's going to ask you about a mid-sagittal section of the brain. So you're going to need to identify mid-sagittal sections of the brain. You guys remember when we talked about the neuroanatomy and stuff like that? I told you which image specifically I'm going to ask you on. So make sure you know where those parts are. I'm also going to ask you guys to identify like white matter versus gray matter, right, in a coronal section. And I think that's it. Are we clear? All right. Any questions?